LearningMeasure.tv, science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 7, Radar and Relativity. Hello, I am David Archer, owner of LearningMeasure.tv and LearningMeasure.com. This podcast is sponsored by TradePug.com, GoToMeeting.com, and is part of the Blueberry community of podcasts. What we're going to talk about today is how to measure position and velocity with wave phenomenon using something like a radar or sonar or LiDAR or one of those things that measure distances. And let's say we have some antenna. Let's say we have some airplane coming at us, and we're some sort of air traffic controller, and we need to know where all the airplanes are. So we might have something like a radar, a big antenna pointed at the sky, and it will have its own coordinate system. And it's pointing in some direction, theta phi, and beam some sort of electromagnetic wave pulse towards the airplane. Well, if the airplane is a distance r for the range from the radar, we know that we know the speed of light. This distance, it'll take some time to get to the airplane. That time is the speed of light. The distance is the speed of light times the time is how long it takes. So the time, the round trip time, let's call that t, divided by 2 times the speed of light equals the range. So now that we have r, theta, and phi, we know its position in 3 space. That's what a radar does. Now I'm going to point out in this episode, we're going to discuss things that were covered in previous podcasts. So you might want to go back and look at some of those, especially the one on wave phenomena and the ones at the very beginning, like episode -5 or 4, on definitions of things like measurement equations. And especially the last couple ones where we talked about things like geometry. Okay, geometry is mathematics that's built out of postulates. Postulates are the things in any theory that you just assume to be true. In the case of a physical theory, like something out of physics, which we're going to talk about in a minute, there are also postulates that people have come up with to build the theory out of. And the validity of the postulates, any postulates in any theory, cannot be proven. All that you can do is verify that the postulates you have lead to conclusions that are consistent with observation. Well, one of the postulates of relativity theory is all observers measure the same speed of light. The speed of light is the same for all observers. It sounds reasonable enough. It has some interesting consequences, as we'll see in a minute. So we know the speed of light is the same for everybody. Once that we've established that's true, you can use that to define, let's say, the meter in terms of the second, which is exactly what has happened. So we now have this way of measuring distance because we know the speed of light and we know it's constant and we know all observers see the same. So we can come up from this, we can also come up with the velocity. We can come up with the radial velocity, r dot, or it was dr dt, dt, which is approximately equal r. Let's say this thing's putting out pulses with a period of t0, and it's putting out a bunch of them. Okay, so the radial velocity is going to be the range, an approximation for some time t is the range at some further time, future time, one period later, r of t over t0. This is one way you can estimate velocity from range. Okay. It's approximately equal to the change in distance over one period divided by the period. So if it moved 1 meter in 1 second, its velocity over that interval, average velocity, is 1 meter per second. We've seen this before. Okay, so you could measure velocity that way. It turns out that's not very accurate. It's very noisy. We talked last week about something called the Doppler Shift, and we're going to cover that in a minute. But one can point out we can get it this way too, but it's not very accurate. But before we get to that, got a little business to take care of. Do you spend more time traveling to meetings than you do actually meeting people? If your time is valuable and who isn't, then you need GoToMeeting. With GoToMeeting, you can instantly meet with anyone. All you need is a PC and an internet connection. During the meeting, your attendees can see your computers and can see their computers, what you show on your PC. It's like you're in the same room. Plus, it's totally interactive. You can all work together, make changes to the report, add slides to the presentation, maybe teach somebody relativity theory. Think of the time you'll save. No more driving or flying to a meeting. Plus, you can hold as many meetings as you want for one low flat rate. It's a real money saver. The next time you're waiting in line at the airport, being ready to be illuminated by your radar from your airport, you could be at a meeting instead. So sign up right now to try GoToMeeting free for 45 days. For this special offer, visit gotomeeting.com/podcast. That's gotomeeting.com/podcast. Try it free now. Okay. I'm always for not traveling if you don't have to, although sometimes it's fun. So you're traveling on this airplane, and you've got this one velocity estimate, and you have a range estimate, but you probably want a better velocity estimate than what you can get from that. Well, let's start to talk about something called the Doppler shift. Well, we know, let's say we have, I better draw my airplane again. And you have some plane wave from your radar that you're coming out of your antenna. Let's say it's pointing right at the antenna, so we don't have right at the airplane, so we don't have to worry about coordinates. So a plane wave is something like, let's say it's a plane wave that looks like this. E to the ikx plus omega t. We've seen this before, wave phenomena. Well, so its phase here, is kx plus omega t. Well, we can ask the question, what's the frequency of the radar? What frequency does the airplane see? Well, we know from a previous episode on wave phenomenon, frequency is this. We can get frequency from 1 over 2 pi dphi dt, or the change of phase. Well, this is a situation when you're on the plane, or when you're looking at the frequency at the plane, both this is changing with time and this is changing with time. So dphi dt is equal to k times dx dt plus omega. Okay, so 1 over 2 pi dphi dt equals, well, this is 2 pi over lambda, so 1 over 2 pi times 2 pi over lambda is 1 over lambda. Now dx dt is v, that's the velocity, rate of change of position with velocity. This is 2 pi frequency, 1 over 2 pi that is frequency. So now we'll call this the frequency at the airplane. It's equal to the frequency, well, let's call this frequency of the transmitter times v over lambda. Okay, before I do that, okay, this lambda, right? lambda equals c over f. So this equals v over c f plus f. So we'll call this f transmitter, and that's 1 plus v over c. So the frequency seen by the airplane is faster, is higher as you're moving together. Well, now you can say, okay, that's the frequency the airplane sees. That's the frequency that's incident on its skin. That's the frequency it reflects. So now you can reverse the argument. Now you can say this is the transmitter emitting this frequency. You can go through the exact same argument and come up with the frequency at the radar, the received, is this, the frequency at the airplane, times 1 plus v over c, times another factor of 1 plus v over c. Okay. Now, this is equal to, so we've got the thing, the received frequency, we'll call it FR here to make it easier to write, is equals F transmit times 1 plus V over C squared, which equals frequency transmit times 1 plus V over C plus, 1 plus 2V over C plus V squared over C squared. Since this term is really small, since most velocities are smaller than the speed of light, this is approximate, you can sort of ignore this term, and this is approximately equal to transmitter frequency plus 1 plus 2V over C. Okay. That's kind of interesting, but it's wrong. And it's not too far off. There was something wrong with my argument here. Now you might have go, what's wrong with it? Well, let's go into that. Okay. This whole time we've assuming that the time seen on the airplane is the same as the time on the ground. That's not right. And I'm going to give you why that's not right in a minute, starting with the postulate that everyone measures the speed of light's the same for everyone. Let's say you're on the plane. And I'll draw the plane a little bigger. And in the plane, you set up 2 mirrors. You want to set up a clock. And you put a light pulse up, light pulse comes down. This distance is L. So we figure out the one-way trip time by we put something here that detects when we send the pulse out, and another thing that detects when it comes back. We measure the round trip time and divide by 2. Well, we know the speed of light's the same for all observers. So this is CT, we'll call this CT airplane. Okay. So he measures this. But you're standing on the ground watching the airplane, and this time, and you're saying, what you see is the light, everything moving. Okay, so this distance here is 2, so it's 2 times the velocity times the time on the ground, right? This is L, okay, which is equal to, so this is equal to VT ground. L is equal to CTA, okay. So, but it's from the ground, you see the light go this path, which is CTA squared plus VTG squared. Pythagorean theorem, which still works. Okay. What does that tell you? Well, L's the same whether you're on the ground or whether you're in the airplane. And one way of looking at that, let's say you had I don't know. Let's say you were blowing out smoke and making smoke trails. As this plane goes, you're making some sort of thing that goes like this. Well, whether you're in the plane or on the ground, you're going to see that same distance. It's L. So, right, the time to go up and down here is t ground, right? Or time to go up is t ground. Because it's going, because it's going this way, that time is equal to this, right? So you can take out the c, and so this is ct, right? It's c, okay, ct ground, okay, let's do it this way. ct ground is this, right? Square root L squared, so C, T ground, this is L, right, that's what that's where I made a mistake. Okay, T ground is equal to 1 over C times this, right, which is CTA squared plus VT ground squared. Okay, now you can do some algebra. And you've got T ground squared equals TA squared plus V squared over C squared T ground squared. So after much algebra, you end up with this. The time on the airplane is longer than the time on the ground by this factor here. In other words, when you're on the ground, you see the airplane's clock run slow. You say, what does that do for the frequency that's emitted at the airplane? Well, you can't just take, you now have a situation where the frequency seen at the airplane is different by this factor. So you've basically got F airplane instead of being this, it's not equal to F transmitted times 1 plus V over C. Instead, it's equal to frequency transmitted times this is 1 minus, sorry. This is frequency transmitted times 1 plus V over C times the square root of 1 minus V squared over C squared. Okay. Well, okay, that's a small difference. What does that mean? Let's take that through to its consequences. Okay, so you can make the same argument for now, if the airplane is this, you can consider now the airplane, the source, and the ground moving towards it, do the same thing, and you get an F at the radar is this thing here times 1 plus V over C over square root of 1 minus V squared over C squared times another one of these, right? 1 plus V over C square root of 1 minus V squared over C squared. Well, this is equal to, we'll do some algebra here, 1 plus V over C times 1 plus V over C over 1 minus V squared over C squared. But this is equal to, with a little bit of algebra, 1 plus V over C times 1 plus v over c times 1 minus v over c times 1 plus v over c. Okay, this is equal to that. These terms cancel, and you got f at the radar is equal to 1 plus, okay, sorry, there's a ft here that should have kept going, is ft 1 plus v over c or 1 minus v over c. Well, let's see how different that really is. But before we do that, we'll have another word from our sponsor here.
One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories and sign up through that link. Each publication subscribed to through this link on LearningMeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support.
Sponsors. Okay, now that we're back, we now have this new formula. F radar equals F transmitted times 1 plus v over c over 1 minus v over c. Well, it turns out there's a formula for 1 over 1. This v is always less than the speed of light. And there's a formula from mathematics of 1 minus x, 1 over 1 minus x, well, is equal to 1 plus x squared plus x plus 1 plus x squared plus x cubed, dot, dot, dot. So this equals ft times 1 plus v over c times 1 plus v over c plus v over c squared plus v over c cubed. Okay, just some basically approximation formulas. Well, this is approximately equal to, let's just do a few terms. We got 1 plus v over c times v over c plus 1 plus 1 times v squared over c squared plus, cubed, vc times, so we got a vc times vc here, so we got another v squared over c squared, v over c squared. So we got this one and that one, and there's other terms. So this is equal to frequency of transmit times 1 plus 2v over c plus 2v squared over c squared plus dot, dot, dot. Well, this looks an awful lot like this. It actually looks an awful lot like this, except it's missing one term, 1v over c squared, plus a whole bunch of smaller terms. So again, if you use this underlying theory that's just assuming time's constant, you get something that's really accurate until this term starts to be significant in terms of your uncertainty. And that does happen in some experience. It doesn't happen with airplanes. But you know, if your measurement, this is a case where your underlying theory might give you a good approximation So, but you're missing something from a more general theory that you might have to add into your measurement equation later. So this is a bit math-heavy episode, but I think it hopefully will be of some interest to you guys. I'm going to probably continue on with radar next week and go on doing a little bit more with radar and maybe a little bit with relativity. So again, I really want feedback from you guys. If you guys have questions on measurement or any topic in science that has to do with anything that has to do with measurement, send me an email at suggestions@learningmeasure.tv. I really want your feedback. I want to know what questions you might have. It might be in a completely different area than what we've covered so far. That's fine with me. I really want some feedback. Also, if you want to be on this show, I really do want to get people who have test and measurement equipment to come onto this thing and show your latest stuff, because I want to have that part of the podcast as well. So you guys send me an email at vendors@learningmeasure.tv. So we'll see what we do next week. I think I'm going to continue on with a little bit with this radar stuff, unless somebody sends me a suggestion. So, all right, that's it for this week. Have a good week.